awak. Awak yang tu lah. Jangan lupa subscribe channel kita. Tanda sokongan. Terima kasih. Hai, Assalamualaikum. Jom kita revise sambil berehat. Sambil berehat pun, kita boleh belajar tahu dengan tengok handphone. Apa tunggu lagi? Jom kita mula. Hai, Assalamualaikum. Jadi dalam video kali ini, jom kita sambung untuk buat soalan dari subtopik 8.4 iaitu angular momentum. Okay, but before we start, so now look at the short notes about the angular momentum. Okay, so the symbol for the angular momentum is given by L, where L is equal to I omega for a rigid body, where I is the moment of inertia of the rigid body and omega is the angular velocity. Okay, but for the particle, we also can calculate the angular momentum for a particle where the equation is equal to mrv, and as we know that equation of v that related to the angular velocity is equal to r omega. So from here, when we substitute L is equal to mrv, mr, where v is equal to r omega, so L is equal to mr squared omega. Okay, so the unit of the angular momentum is kg meter squared per second. And in this subtopic, we also learn about conservation of angular momentum. So the definition of conservation of angular momentum is the total angular momentum of a system about a rotation axis is constant if no external torque acts on the system. So we can write that total momentum initial is equal to total angular momentum final. So I initial omega initial equal to I final omega final. Okay, sekarang kita tengok pada contoh ini, kita ada seorang lelaki duduk di atas kerusi, right? Okay, so what happened when the position of the mass, okay, ataupun dumbbell dekat sini, okay, is changing. Okay, initially, let's say this is the initial case. Okay, you can see if this is the axis of rotation. So now we can see here that the position of the mass from the axis of rotation is given by r. Okay, and this is also r. So what happened when the mass is located close to the axis of rotation? So here we can see that, okay, the distance between the mass and the axis of rotation is reduced. Okay, so initially we can see here that the moment of inertia, okay, is equal to the moment of inertia for the man, okay, ataupun saya tulis the moment of inertia of a body plus the moment of inertia for the mass 1 plus the moment of inertia for the second mass. Okay, and remember the moment of inertia of m1, okay, is equal to mr squared. Therefore, if r is decreasing, okay, so I also decrease. Okay, so we can write that I final would be equal to I of a body, which is for the man, plus, okay, I m1 plus I m2. Okay, but for the final case, since r is decreasing, so I also decrease. Therefore, the final moment of inertia should be decreased. Okay, so when r change, I also change. And what happened? Of omega, omega also changing. So in this case, we can compare. Okay, so omega initial, okay, I initial omega initial is equal to I final omega final. And then we can write that omega final should be equal to I initial omega initial over I final. So now look at here, since I final is decreasing, okay, so the final angular velocity should be increased. Okay, so this is the simple explanation, okay, about the relationship between r I and omega. So now let's proceed to the first example. Okay, so let's say here we have a merry-go-round. Okay, for example. Okay, and this is the center. Okay, so initially a child sits here, okay, at the center. Okay, while the radius of the merry-go-round is given, okay, and it is 2 meter. Okay, so this child will walk out the edge, means that dia akan jalan, okay, from here, okay, until here. Okay, so if the merry-go-round has a rotational speed, so this one should be 0.2, so the unit should be radian per second. So betulkanlah. When she is at the center, maknanya masa dia dekat tengah-tengah, omega ataupun rotational speed is 0.2 radian per second. What is its rotational speed when she gets to the edge? Okay, so kita bolehlah tulis. Okay, conservation of momentum, angular momentum, initial is equal to final. So I initial omega initial is equal to I final omega final. So now we want to calculate omega final. We can straightly substitute in this equation. Okay, so now look at here. I initial is 500, so it's given. Maknanya masa sebelum budak ini pergi ke tepi merry-go-round ni, so kita hanya ada moment of inertia of the merry-go-round, okay, which is 500 kilogram meter squared. Jadi moment of inertia budak ini pula berapa? Kalau kita tulis the moment of inertia for the child, okay, dekat sini kita tak kira lah. Okay, sebab dia at the center. Okay, dia dekat axis of rotation. So, kosong lah. Sebab formula dia IC is equal to MR squared. Okay, so tak ada lah moment of inertia for the child. So, initially, okay, we just consider the moment of inertia, okay, for the merry-go-round, which is 500 kilogram meter squared. Okay, and initial angular velocity, we can substitute here. It's given 0.2 radian per second, and I final. Now, okay, we need to know what is the I final here. Okay, so I final, okay, this is the I final. So we can calculate I final is equal to I, the merry-go-round, plus I for the child. Okay, so merry-go-round tadi kita dah tahu 500, but the moment of inertia for the child we can calculate where it is equal to mr squared. Okay, di mana kedudukan budak tadi berada di sinilah, which is 2 meter from the center. Okay, so we can substitute here. So the mass of the child is 25 kg, sorry, and r is 2 squared. So the final moment of inertia for the whole system should be 600 kg meter squared. Okay, so you can substitute here 600. Okay, and then after calculation, you will get the final rotational speed when she gets to the edge. So it is equal to 0.167 radian per second. Okay, so finish example number 1. So now example number 2. So here we have a satellite that is rotating once per minute. Okay, so means that we have the information about omega, where omega is equal to, bila kata once per minute, means that 1 revolution per minute. Satu putaran lengkap dalam masa 1 minit. So we need to change revolution and minute into radian per second. So, okay, saya buat darab silang. Revolution dekat atas, revolution duduk dekat bawah. So, 1 revolution is equal to 2 pi radian. So, we can cancel revolution and then minute. So, 1 minute is equal to 60 seconds. Okay, so we can write that the initial angular velocity of the satellite, okay, is equal to, kita boleh kira lah. Okay, iaitu bersamaan dengan 0.105 radian per second. Okay, and given that the moment of inertia for the satellite, we write as S. IS is for the satellite. Okay, initial lah ataupun I naught. Okay, kita boleh letak I naught 10,000 kg meter squared. Okay, so now Erin, an astronaut, extends the satellite solar panel and she increased the moment of inertia for the satellite. So you can write that I final, so daripada 10,000 to 30,000 kg meter squared. Okay, so how quickly time taken so dia suruh kira time dekat sini. How quickly is the satellite now rotating to complete one revolution? Okay, after the moment of inertia is increasing. Okay, so what happened to the period, which is the time taken to complete one revolution? Okay, so we can use the conservation of angular momentum, where total Li is equal to total Lf. Kenapa? Sebab saya nak cari omega final. Okay, so from omega final, we can use this equation equal to 2 pi over t. Okay, so idea dia dekat sini, kita nak cari t. Okay, so I initial, okay, omega initial equal to I final omega final. So omega final is equal to, okay, I initial, which is 10,000 times omega initial 0.105 over I final, which is 30,000. Okay, therefore omega final is equal to 0.035. Okay, 0.035 radian per second. Tapi soalan bukan tanya final angular velocity. So we want to find what is the time taken. Yang barulah. Okay, how quickly, okay, to complete one revolution. So we use omega final is equal to 2 pi over t. So from this equation, okay, we can find t, where it is equal to 2 pi over omega. Okay, omega ni omega final tadilah. Sebelum kita increase the moment of inertia for the satellite, okay, it is rotating once per minute, macam tu. Okay, maknanya dia boleh complete one revolution dalam masa 60 seconds. Okay, tapi bila kita increase the moment of inertia, it will affect the period, which is the time taken to complete one revolution. Okay, so omega final 0.035. So press your calculator, you will get t is equal to 179.5 seconds. Okay, so finish example number 2. Okay guys, example number 3. So here we have a flywheel that rotates without friction at an angular velocity of 600 revolution per minute. Okay, so remember to change the unit into radian per second first. Okay, so what happens? So this is the first flywheel and this is the second flywheel. A second flywheel which is at rest and has a moment of inertia 3 times. Okay, 3 times, which is 3 I naught, 3 times that of the rotating flywheel. Kalau saya kata apa, kita nak tulis macam ni lah, I1. Ini adalah I2 kan, I2 which is 2 kali atau 3 kali I1. Okay, macam tu. So A, use the law of conservation of angular momentum to determine the angular velocity omega of the combination. So soalan bagi tahu dekat sini, because the friction exists between the surfaces, the flywheels very quickly reach the same rotational velocity after which they spin together. Okay, so means that we can use that L initial is equal to L final. Okay, and I initial, omega initial equal to I final omega final. Okay, but before that, don't forget to change omega naught 600 revolution per minute tukar kepada radian per second. Okay, cuba buat. Okay, cuba tukar. You akan dapat omega naught is equal to 62.83. Okay, radian per second. Alright, so now we want to calculate omega final. Okay, here should be omega final. So omega final is equal to I initial. Initially inilah. Ini initial. Sebelum tu dia seorang je yang berpusing. So kita hanya ada I1, iaitu flywheel yang pertama, flywheel 1. Okay, I initial times omega initial, kita dah kira tadi 62.83 over I final. Okay, so now I final here referring this state. Okay, so final dekat sini. Okay, where we have flywheel 1 and flywheel 2. Okay, so now let's calculate the final moment of inertia. So I1 plus I2. So I1 lah plus I2 adalah 3 kali ganda I1. Okay, so I final should be 4I1. Okay, so we can substitute here 4I1. Alright, so we can see here we can cancel I1. Alright, and then let's calculate omega final. So the answer should be 15.7 radian per second. Okay, so finish example number 3. Alright, example number 4. So I think this is the last example for this video. So here we have a person stands at the center of a horizontal platform which can rotate about a vertical axis as shown in this figure, right? Okay, so the person holds a weight with each hand and with arms stretched out. Okay, like this one. So the platform is then made to rotate with constant angular velocity. So if the weights are brought towards the body, okay, like this diagram, okay, as shown in figure 2, explain what will happen to the rotation of the person. So we need to explain, okay, what will happen to the rotation of the person. So as we have discussed before, okay, in this case, the initial moment of inertia. So dekat sini kita ada contohlah moment of inertia for the boy. This is the moment of inertia for the first mass. And this is the moment of inertia for the second mass. Okay, and you can see here, okay, this is the axis of rotation, for example. Okay, and the position of the mass M1 and M2 from the axis rotation can be written as R. Okay, macam tu. So in this case, we can calculate what is the initial moment of inertia. So maknanya initially kita ada I of the boy plus I of M1 plus I of M2. Okay, and then for the final condition here, okay, when the weights are brought towards the body, so what happened? Okay, you can see that the R, okay, the distance between the mass, okay, to the axis of rotation is decreasing. Okay, so we can write that I final should be equal to I of the body plus I M1 plus I M2. So since the moment of inertia M1 and M2 can be write as mr squared because we can treat as a particle. So since the moment of inertia for mass 1 and mass 2 can be write as mr squared, so since the value of R here decreasing, kan, berkurang kan, so dia dah semakin rapat ni kat sini. Okay, dia semakin rapat dengan axis of rotation. Okay, so when R is decreasing, therefore I also decrease. So the moment of inertia here should be decreasing. Therefore, the moment of inertia final is also decrease. Okay, alright. So we can write that when the weights, okay, so brought towards the body, okay, R is decreasing. Okay, so the moment of inertia M1 and M2, okay, also decreasing. Okay, since we can see here that I M1 is directly proportional with R, and I M2 also directly proportional with R. Alright, so now we can write that the moment of inertia final is less than the moment of inertia initial. Okay, so based on conservation of angular momentum, okay, so I initial omega initial equal to I final omega final. Alright, so we can write that omega final is equal to I initial omega initial over I final. So since I is decreasing, so what happened to the omega final? So the angular velocity should be increased. Okay, so we can write that omega final is bigger than omega initial. Okay, since I final less than I initial, so means that omega final must be bigger than omega initial. So apa yang kita boleh tulislah kesimpulannya? Okay, we can write that, okay, since I final, okay, is less than I initial, therefore, okay, omega final is bigger than omega initial. Okay, buat I naught pun boleh lah, ataupun I. Okay, you nak buat omega naught boleh, you nak buat omega I pun boleh lah. Okay, so, okay, the person will rotate with higher. Okay, since omega final bigger than omega initial, so the person will rotate with higher angular velocity. Okay, so this is the answer for question A. And how about question B? Okay, so saya nak jawab dekat sini lah. Question B. Okay, so here we have a scatter spins at initial angular velocity omega. Okay, omega 1 is 11, okay, radian per second. Okay, with her arms outstretched. Okay, maknanya macam tadilah, macam gambar yang lelaki tadi ni. Okay, the arm outstretched. The skater then lowers her arms, thereby decreasing her moment of inertia by a factor of 8. Okay, jadi kalau tengok kat sini, dia kata the skater then lowers her arm. Okay, maknanya tangan dia bawa masuk ke dalam lah, dekat dengan axis of rotation. Okay, kita dah tahu tadi, dekat sini pun kita dah nampak, I final, automatically the moment of inertia, okay, of the skater should be decreased. Okay, tapi dia dah bagi decrease by berapa? Okay, I final, okay, decrease by factor of 8. That's mean I final is equal to I initial over 8. What is the skater's final angular velocity? So now we want to calculate what is the omega final. Okay, so I initial omega initial equal to I final omega final. So now we want to calculate omega final, and it is equal to I initial omega initial over I final. Okay, so I initial kita tak tahu berapa, kan? Kita tak tahu berapa, tapi kita boleh rearrange this equation. Okay, so I initial is actually equal to 8 I final. Okay, so maknanya dia kata tadi kita kena faham ni kat sini. Okay, the moment of inertia decreasing, okay, by a factor of 8. That's mean 1 over 8. Okay, maknanya final dia akan decrease by a factor of 8. Okay, so bagi 8 lah sebab dia decrease. Kalau dia increase adalah 8 kali ganda tu lain. Okay, so divide 8. So now I naught is 8 IF times omega initial is 11 over I final. So we have unknown here, we can cancel out. Okay, therefore omega final is equal to 88 radian per second. Okay, so this is the answer for question 4B. Alright, so for this chapter, I think I will stop here. So finish chapter 8, and for the next video we will continue with chapter 9. Alright, so good luck for your assignment. So see you in the next video. Bye bye.